So there's going to be some naming on this particular test because we talked about a bunch of different naming. And one naming that we did talk about was alcohols. So in this case, we have 2 alcohols, so this would be a diol. And we want our parent to contain our alcohols as much as possible. Now remember, the oxygen of the alcohol should not be included in your numbering of your parent because it's not a carbon. So our parent has 1, 2, 3, 4, 5, 6, 7, 8. So this is an octane diol. And our oxygens, our alcohols, should be on our lowest numbering system possible. So that would be numbering from this way, putting one of our alcohols on 1. But remember, don't number the oxygen. So this is an octane 1,3-diol as our total parent name. And then we do have a methyl and an ethyl. And remember, we put these in alphabetical order. So E comes before M. So we have 3-methyl. And 6-ethyl. Now lastly, we do have 1 stereocenter. Carbon-6 is not a stereocenter, but carbon-3 is. So oxygen is clearly going to be 1. That one's pretty straightforward. And then my methyl is my lowest, because we have a tie, carbon, 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 but then we have 3 hydrogens. So 4 is back, so we're good there. Now we do have a tie between going out between a carbon and a carbon. So we have to try to break that tie. So this is just a little review. So this carbon has 1 carbon and 2 hydrogens. This carbon has 1 carbon and 2 hydrogens. So our first layer is also a tie. So we got to go to the second layer in this case. So when we look at the second layer, this carbon is attached to a carbon and 2 hydrogens. This carbon is attached to an oxygen and 2 hydrogens. So that oxygen wins. So this will be my number 2. So this one will be 3. So that is, of course, R. And you can put the 3R, but this is the only stereocenter, so I don't need to. Okay, so whenever you see lithium aluminum hydride, whatever it's reacting with, it is a source of H negative. H negative is both a strong base, so we usually can't have too much protons here. So an OH would be reactive. And H negative is going to be here a strong nucleophile. So our lithium aluminum hydride is a source for our hydride. So what we have is a strong nucleophile. Our hydride is going to react with our strongest electrophile. So that'll be this partial positive carbon that's between 2 partial negative oxygens. So we will get an attack, and then we will push the electrons onto the oxygen. Remember, we do not have a straight SN2 reaction because that doesn't occur very well in an sp2 carbon. So instead, the electrons get pushed onto our electronegative oxygen. And under these strong, basic H negative conditions, we're only going to form negative charge. So I'm drawing this hydrogen bond. You don't really have to draw it, but I want you to see where it is. So under these conditions, strong basic conditions, oxygen is an okay leaving group as O negative. So that's what's going to happen. We're going to reform our carbon-carbon double bond, and we're going to lose this alcohol. Well, it's going to lose as a alkoxide. It'll form the alcohol when we throw water in. So again, you don't have to draw this hydrogen, I'm just showing it so you can see it right now. Now we can have another addition of H negative because we have a lot of these floating around. And it's going to again attack for a second time. And again, I'm showing the hydrogens, you don't necessarily need to, but I'm just being clear. And we still, of course, have that alkoxide floating around because it's not doing anything. So once this occurs, now we can throw water in, because we can't throw water in until the reaction is complete, otherwise we're going to get a mixture of products and it's not going to be useful. So now we can show the last step, which is water reacting with our alkoxide to form our alcohols. Sodium borohydride isn't a strong enough H negative to react with an ester, so we won't get a reaction. And we only get this one addition of hydrogen if this is a carbon, because carbon is not a good leaving group. So that's why esters and carboxylic acids undergo this 2 addition to form the primary alcohol, because they're okay leaving groups. Carbon's never a good leaving group. Any questions? Here, this is just an SN2 reaction where we're replacing our alcohol with a chlorine. So we talked about a couple of different reagents, and I would accept any of them. We talked about a couple of different reagents for an SN2 reaction with bromine as well. So SOCl2 is one with pyridine. Another one we talked about is HCl and zinc chloride. Or you can tosylate it to make your alcohol a good leaving group, followed by reaction with our strong OH nucleophile. I'm sorry, chlorine. Whew, I don't know where I'm getting that OH. So our Cl negative. All of those work, I'd accept any of them. And we had talked about a couple of different reagents for an SN2 reaction with bromine as well. Now looking at B, what we see is a carbon-oxygen double bond and a Grignard. Now don't put an extra carbon. This BRMG, the way it's written, is the same as writing it like this. Because it's kind of a right between an ionic and a covalent bond. So you can draw it both ways. And I think it's easier to see drawn this way. So we do not have a carbon between that carbon of the benzene ring and the magnesium. So don't add an extra carbon. That's a common mistake. So we're going to get a tack, and that's going to push the electrons onto the oxygen. The water protonates it. So what we form is our alcohol. Oh, you don't do that. Now do protonate this because you do not isolate O negative. And we have our new bond, our carbon-carbon bond between our benzene ring and the carbon 1 of our starting material. What I don't want to see, I don't want to see this because oxygen does not exist in that manner. If it wasn't protonated, it would have a formal charge. But that's not really something you're going to isolate. Once you throw in the water, that's going to be protonated. But without the charge, it's just wrong. You must show formal charge. So you have to show it as the alcohol. I don't want to see that. Any questions with the Grignard? And of course, that carbon 1 is our partial positive carbon. That's why the Grignard attacks there. What we're looking at here is a bunch of reducing agents with different reactivities. So the first thing that we want to consider is our different functional groups. We have a carbon-carbon pi bond here. We have an aldehyde, and then we have an ester. And we just did that mechanism. I gave you the answer of how lithium aluminum hydride reacts with an ester up here. It's right here. Same reaction. Except that instead of forming two alcohols, the alcohols are tethered together. But it's the same reaction. So first off, let's look at lithium aluminum hydride. That's not going to react with carbon-carbon pi bonds, and neither is sodium borohydride. So neither of those are going to react with that carbon-carbon pi bond. However, lithium aluminum hydride will react with our aldehyde and our ester. But it won't react with our carbon-carbon pi bond, so that stays the same. And numbering here is going to be really helpful. So I'm just going to draw my backbone carbons. Nothing happens to my carbon-carbon double bond, so I'm just redrawing it. That's a hydrogen. When our H negative attacks here, again, we're going to push the electrons up, and we are going to have this as our leaving group. Just the same way as our other reaction did. It's the same mechanism, except that the R groups are tethered together. We just did that mechanism. But what's the difference? Our R groups are stuck together. So they're still going to be stuck together. And then, of course, we get that second addition of hydride. Just like in the example that we did for that mechanism. So the amount of carbons that's tethering that alcohol together is dependent on these carbons. So we have 1, 2, 3, 4. So this is an alcohol. And we also have an alcohol on 4. So this is our leaving group, but it's still stuck. So this bond breaks when our leaving group leaves. And then, of course, that aldehyde will also reduce. Everyone see that? Again, same thing as before, but the alcohol is still stuck. The connectivity of my carbons does not change. If we look at sodium borohydride, again, we won't reduce the carbon-oxygen double bond. It's also not strong enough to reduce the ester. So we're only going to get reduction at the aldehyde. Everything else stays the same. And it's common that you draw that hydrogen of an aldehyde. You don't necessarily have to, but it's a very specific hydrogen, so often it is shown. I think one NMR, we have very specific where hydrogen comes out, but it also looks more visually appealing to have it there for some reason because of symmetry, so it is often shown. Lastly, H2 and platinum will reduce all pi bonds. So it's going to reduce the carbon-carbon pi bond, the aldehyde, and the ester. So the only difference between the lithium aluminum hydride product and the H2 and platinum product is going to be that pi bond is gone. So we reduce the carbon-carbon pi bond as well. Oh, I didn't reduce my, there we go, my aldehyde. I said we reduce it, and then I didn't draw. Also notice the number of carbons are not changing with any of these products. Know your difference in selectivity. Now there's really no reaction that we're talking about now that will reduce an ester and not reduce an aldehyde or a ketone. Now we will talk about some later on and how we can do that, but as of now we have not learned how to do that. Here is a synthesis problem. First thing to note, we have a new carbon-carbon single bond. We're clearly not going through a triple bond because there's no way to make one. So we must be going through a bridge. But we have an alcohol present, and it's present at the end, so we're going to have to protect it. Don't make this harder than what you have to. We already have a halide. Just make it a Grignard. Just add magnesium. But you do have to protect your alcohol. A Grignard will not happen in the presence of an alcohol. Also, our new carbon-carbon bond is on the same carbon as our alcohol. So we know we're going through acetyl bond O and not an epoxide. But at the time, we hadn't talked about epoxides. But you still should be aware of that because of the difference. But right now, only the things that we learned Grignard reacting with has been a carbon-oxygen double bond and an epoxide. And if it was reacting with an epoxide, the alcohol would be at one adjacent carbon. So the first thing we need to do is protect our alcohol. So we protect that with TMSCl. Now, not TS. TS makes it a good leaving group. And pyridine and or triethylamine. So that's going to protect our alcohol. Basically, we are removing the hydrogen so it cannot react with our Grignard reagent. Because remember, the carbon with a negative charge is a very strong nucleophile, but it's also a pretty strong base. And it will act as a base because it's easier because of sterics. If there's any acidic hydrogens. So now we can make this a Grignard by just throwing in magnesium. Remember, don't add any extra carbons. That's a specific reaction. Okay, so now we can react our Grignard. We are adding 1, 2, 3, 4, 5, 6 carbons. And we're adding that new bond between our ring and carbon 1. So that means our functionality has to be on carbon 1. And we have 3 possibilities of that. So first off, why isn't it the alcohol? If you took your Grignard and reacted it with the alcohol, then all you would have is the acid-base reaction. And your R group would no longer be reactive. And a couple of you protected the other alcohol and then threw in an alcohol. So think about what you're doing. You're protecting the alcohol because the Grignard reacts with an alcohol. So you can't react it with an alcohol because it's not going to give you the reaction you're trying to do in the first place. So don't just memorize, oh, if I have an alcohol, I have to protect it. Understand why. So this is not our carbon source. And of course, this one isn't, and this one isn't, and this one isn't, because they aren't connected right or don't have the right amount of carbons. What about the alkyl halide? Why wouldn't that work? In theory, we should be able to have an SN2 reaction with an alkyl halide. But in practice, because it's just not as partial positive as acetyl O, instead we likely get the E2 instead of an SN2. So we just don't get a good yield with an alkyl halide. In theory, it's an electrophile, but it's not a good enough electrophile. Only because the bromine is also a good leaving group, and therefore we can just get an E2. We can't get an E2 with acetyl-1O because we have acetyl-1O. Oxygen's not going to just leave. So the E2 is not really accessible so much with that one, but with the alkyl halide it is. So it's just not going to give you a good reaction. In theory, our R negative should react with an alkyl halide, but what actually happens is we get the E2 reaction, and again, RH. So again, our Grignard would rather act as a base. So what we need is to react it with acetyl. So that's going to be our reagent. Remember, you must add water second, because again, we can't have any acidic hydrogens. So then we're adding water. Bless you. Our last step, well, if I'm really careful, my TMS group can still be protected. I could technically do things like oxidize this and not touch that. So I could still do stuff like that. But my final product has the alcohol. So all I need to do is deprotect to get to my final product. Everything else is in my final product. So we can deprotect with TBAF, that's just our source of F negative, or H3O plus. And that will deprotect it. Any questions with that synthesis? It seems a lot easier when I explain it, doesn't it? The more you practice, the easier it is. You really can't just read the notes in this class. You have to go through examples. Yes?
How is that having 2 to 3 steps when it's just 4 per year?
Technically, what you often see is that this isn't really a separate step because you can't isolate this. I'm showing it so you're clear and you're seeing what's happening, but usually what you see is 1, 2, 3, and the reason why is you cannot isolate and characterize this because as soon as the atmospheric air hits it, it's going to react with water in the air and be used up. So technically this is all one pot. We take this, we throw in magnesium, we let it stir for a while. Then we're going to add this, let that react for a while. Then we're going to add this. Conversely, here to here, we're going to mix this all together, isolate this, take an NMR of it, take TLC of it, make sure it's clear, get a percent yield, and then go on. So technically that's all one step. I'm just drawing it separate so you can clearly see what's happening. And also, you might, instead of H2O, you can just add H3O plus here to remove this protecting group. Because just a little bit of acid will pull that off really easily. Okay, on to the next quiz, more naming. So we learned a bunch of names, including sulfurs, which aren't on this quiz, so you need to make sure that you know them. And I didn't really have room on quiz 7 either to put any naming of sulfurs and thiols, so make sure you know those namings. A thiol, if it is the part of the parent, then it is a thiol, instead of all like alcohol is thiol. But if you have a more reactive functional group like an alcohol or something like that present, then it's a substituent and it's mercapto. So know the difference, yeah?
I have a question about that. The only thing that would be more is, but an ether too, right? Would be more.
Usually because naming an ether as the parent is typically too difficult. Usually, if you have a compound that has a thiol and an ether, like a salt SH and an ether, you're likely going to not name the ether as a parent because it's going to be too complicated. Most of the time, unless if it's really, really simple ethers, diethyl ether, ethyl methyl ether, like no other functional groups but R groups, then you're going to name it with the method we're going to talk about here, where you name the ether as a substituent, because it's just easier. So anything that's more complicated than two really simple R groups on the side of the oxygen, you're going to use this route. So in that case, you could name the thiol as the parent, but usually alcohols will take priority. We haven't learned how to name acetyl von O's yet. So pretty much if you see an alcohol, the priority for naming is going to be alcohol, and the thiol is going to be a side chain. That's going to be called a mercaptan. But we're going to learn how to name acetyl von O's. That's going to take priority. We're going to typically priority is given to either the more oxidized carbon, but the carbon of the OH and the SH is the same oxidation state, or the more what we consider more reactive or more common functional group. So that double bonds, alcohols, or triple bonds will be named for the parent, and your thiols will be a side chain. And then the sulfides are just named the same as what we're talking about with the epoxides. So go through those namings because I don't have two examples of those in here. So this is that case where this particular compound A would be way too hard to name it as an alkyl ether. It's just too hard. That other R group is just, there's a double bond in there. It's too complicated. So it's much easier to name this in the second method where our ether is a side chain, an ethoxy group. I'm sorry, an alkoxy group. And this alkyl is whatever number carbons is attached. So our parent is going to be much easier named to contain the carbons that have the pi bond, because it gets too complicated if that tries to be a substituent. So we want our pi bond to have the lowest numbering system possible. So that is a pent 1-ene or a 1-pentene. And that's just our parent. So in this case, it's easier to name our ether as a side chain. So this is our whole side chain. It is an alkoxy group, and the alkyl that we name it is based on the amount of carbons. So we have 3 carbons. What is 3? Propyl, so this is a propoxy. If that was a tert-butyl, it would be a tert-butoxy. If it was a butyl, it would be a butoxy. If it was an isopropyl, it would be an isopropoxy. Whatever the R group is named, that's it with oxy at the end. And then putting that in order, but we don't have any other substituents to put in order, but this would just be an order based on other substituents. So it's just a 3-propoxy. It's propoxy, yeah. So now we just need to name the stereochemistry, and this one is, of course, our oxygen is going to be highest priority. Then we have a double bonded carbon and a single bonded carbon. So remember, we treat our double bonds as if our carbon was bonded to 2 carbons, or 2 of whatever atom the double bond is between. So carbon 2 is bonded to carbon-carbon and a hydrogen, versus carbon 4 is bonded to carbon and 2 hydrogens. So carbon 2 is going to be number 2, and carbon 4 is number 3. And then, of course, we have a hydrogen. It's going back, so we don't have to do anything. This is just S. Here, this one is going to be pretty hard to name as the epoxy as our full parent name. So instead, we're going to put our cyclobutane as the parent. Again, just what's easier. So this one's much easier. It's really hard when the epoxy group is on a cyclic structure to use the other naming way. So our parent is cyclobutane. And we are going to name our epoxide as an epoxy group. The only difference is, instead of alphabetizing, epoxy is always tied with the parent name. So it's always right before, no matter the alphabetical order. Why? I have no clue. But that's the way that it is. They really tried to get a really good systematic naming system with the IUPAC naming system, but there's some little things in it that it's just like, well, you just have to know the way that it's done, because it's kind of weird. So epoxy goes right before the parent name. Now we want the lowest numbering system, and you have to kind of play around with this, but the lowest numbering system will be the one where the two methyl groups are, because then you will have substituents 1, 1, 2, 3, 4. Basically, because that carbon has two R groups on it. So that would be our lowest numbering system. 1, 1, 2, 3, 4 versus 1, 2, 3, 4, 4, or any other of the methods you could find. So remember, bromo comes before methyl. We do alphabetize those. So we have a dimethyl. Oops, I didn't put enough room. And a bromo. Our epoxy is 2, 3. Now we do, unlike double bonds, we do put locate numbers for both carbons that the epoxide is part of. Again, I don't really know why. But that is the correct numbering, the way to name it. Because technically, if it was a 4-membered ring with an oxygen, it wouldn't be called an epoxy. It would be called a different name, so I don't know. Then we have 1, 1 dimethyl. Don't forget, we want both numbers because we have dimethyl and 4 bromo. And lastly, our stereochemistry. Bromine's going to be 1. This hydrogen's going to be 4. Notice hydrogen is coming forward, so we do have to think about that rotation. Then we have a tie between carbon 1 and carbon 3. They're both carbons. Carbon 1 is bonded to 2 carbons and a carbon, so that's 3 carbons. I don't know why I said it that way. And carbon 3 is bonded to an oxygen and 2 carbons. I'm sorry, an oxygen, a carbon, and a hydrogen. An oxygen, a carbon, and a hydrogen. So oxygen wins over carbon. Remember, it's not additive is the first point of difference. So this will be 2, and this will be 3. So that's going to be R. It looks like I drew S, but remember, I have to invert it because hydrogen is coming forward, and it needs to be going back. You can think about rotating it, or you could just do the opposite. Because all we would do is rotate it 90 degrees. Any questions with that naming? So that is the best way. The oxyuran system, where our epoxide is the parent, isn't a very useful system when it's part of a ring. But if it's a linear structure, you can do it. But remember, your parent is the 3 atoms of the epoxide. And then the parent is just oxyuran. But I think that the epoxy route method is easier. Most times. Okay, so here we have a Williamson ether synthesis. So remember, what we're doing, the sodium hydride, the hydride is acting as a base and deprotonating the alcohol. That's a very useful method of deprotonating the alcohol because we form our alkoxide plus hydrogen gas And guess what hydrogen gas can do? Float away. So our byproduct is easily removed because it is a gas. So this is a very useful reaction to form this nucleophile. Now this nucleophile can react with an alkyl halide, but remember it's a strong nucleophile. So the alkyl halide must be primary or methyl because secondary and tertiary are going to lead to predominantly E2. And we don't want E2, we want SN2. So we have to look at our starting materials. This carbon is primary. This carbon is secondary. So our alkyl halide must be this part because that's our only primary carbon. And therefore our alcohol comes from this part. And that's our only row because the alkyl halide must be primary. So my alcohol is this cyclohexanol. And then my alkyl halide. And it doesn't matter which halide you use, is this material. My total carbons for my alcohol plus my alkyl halide should equal my total carbons in my final product. Otherwise, you throw it off. If I tell you this is an alkyl halide, don't give me something else. Give me an alkyl halide. Say, water-containing group with a halogen. If I tell you it's an alcohol, give me an alcohol in the box. Don't give me something else. I'm not trying to trick you. I'm telling you what I want in each box. Okay, here's another example of those reagents that have selectivity. Now this is oxidizing agents. Remember how to calculate oxidation. So oxidizing agents will go for an increase in oxidation number. Typically what we see in carbon-containing compounds is more bonds to oxygen. That's not always true, but for the most part, that's where that oxidation term comes from, is the fact that when it was first really researched and understood, oxidizing agents typically had a lot of oxygen, and usually your compound had more bonds to oxygen at the end, hence oxidation. Now there's definitely oxidation reagents or reactions, especially when we're talking about metals that have nothing to do with oxygen. But that's where that term oxidation comes from. Like, for example, rust forming. That was noted, and what happens with rust forming is the iron gets oxidized and you got more iron-oxygen bonds. So that's why oxidation is called that. So in general, oxidation agents, at least when we're discussing organic chemistry, typically contain a bunch of oxygens. And usually what we do is form more bonds to oxygen from our compound. So PCC and our chromic acid both oxidize alcohols, but they do have different reactivities. Chromic acid is very reactive, and it will react with a secondary oxygen to form a ketone. Because we only have one hydrogen there. It will not react with a tertiary alcohol because we don't have any hydrogens on that carbon. And to get more bonds to oxygen, we have to have a removal of hydrogen. So we don't have any hydrogens there. Primary alcohols, it will react, and that's our difference in selectivity, all the way to our carboxylic acid. We have 2 hydrogens, so we can get 2 oxidations. If we happen to have an aldehyde, it will also react that with a carboxylic acid to a carboxylic acid because we still have a hydrogen available. It can still be further oxidized. But we don't have an aldehyde. This is a ketone, so neither of our oxidation agents are going to touch it because, again, we don't have any hydrogen on that carbon. So we have a tertiary alcohol with no hydrogens and a ketone with no hydrogens, so no reaction is going to happen with those two. So in both products, the ketone is retained and that tertiary alcohol is retained. Because in both cases, the carbon does not have any hydrogens. So we have a secondary alcohol and a primary alcohol. And our chromic acid will take our secondary alcohol and form our ketone. it will take our primary alcohol and form the carboxylic acid. It will not stop at the aldehyde. Notice there is no change in the amount of carbons from my starting material to my product. I have the same amount of carbons to both my starting material and my product. Now, PCC will react with the secondary alcohol exactly the same as chromic acid because, again, we only have one hydrogen, so we can only get one oxidation. The difference in selectivity comes from a primary alcohol. Our primary alcohol has two hydrogens, but PCC will stop at the aldehyde. So we're going to stop at this position. Y'all have a good night. So that's our difference with reactivity, and note your selectivity and reactivity for these. Have a good night, Seth. Have a good night. Yes?
So for a secondary alcohol, whenever you form the ketone, it's just
You don't have, once you form the ketone, you don't have a hydrogen, so you cannot have further oxidation with these oxidation agents. These oxidation agents cannot further oxidize.
so you just get rid of the hydrogen and put a double bond there. And
Yeah, and go back and look at the mechanism in your notes. Understand when the deprotonation occurs. But for these two reagents, you have to be able to remove a hydrogen on the carbon. So if there's no hydrogen on the carbon, no reaction is going to occur. And both of these oxidizing agents have a bunch of oxygens. And again, you can go back and see what PCC looks like. It has a bunch of oxygens. Technically, KMNO4, which we've used as oxidizing agents in the past, can also do the same thing as our chromic acid, but it tends to react with other functional groups, so we won't talk about it again until chapter 21, because it's just really reactive with different things. And when we're talking about oxidation with ozonolysis, we can do that with double bonds and triple bonds, but those aren't reacting here. We don't have a double bond and triple bond. But these two oxidizing agents won't react with carbon-carbon double bonds and triple bonds, which is nice about them. So know that selectivity. Okay, here we're just forming an epoxide. We talked about two different routes. We can use MCPBA, or you can actually draw out what MCPBA looks like, or just put ROO. H, I accept all of that. That's fine. So MCPBA is the specific compound for one of these peroxy acids. Or the other route, and I would accept either, is to react Br2 in the presence of water to form your halohydrin, bromine on one carbon, alcohol on the other carbon. So that's just our addition reaction we learned in chapter 9, followed by reaction with sodium hydroxide, which allows us to deprotonate our alcohol, and that attacks and bromines our aluminum group. So that's the route. Both routes work, I accept either. So they both form the epoxide. They both form, these two things are on the same side, so they're on the same side of the epoxide. Because remember, we don't have free rotation around the double bond. Here we're looking at reaction of HBr and an ether. This is our hydrolysis reaction. Remember, this doesn't work with HF. This doesn't work with HCl. It's too slow with HCl. It's absolutely too slow with HF. With HCl, it's just too slow. So you don't really get much reaction. So this only works with HBr and HI readily. You're going to react with both sides of the epoxide unless you form phenol. Phenol is going to stop. And in this case, we have an oxygen bonded directly to a benzene, so that will form phenol. So in this case, we're not going to hydrolyze that carbon. Otherwise, we're going to completely break up the molecule. But in this case, we don't, because the benzene ring is directly attached. So the mechanism is very straightforward. We have an acid, HBr. That means we have a partial positive hydrogen and a partial negative bromine. The only thing that is somewhat basic in this reaction is our oxygen. So that's what's going to happen. Now, the benzene ring double bonds will not react with the hydrogen. They're too stable. So that's our first step. So what that does, that gives us, and you must show your formal charges. I won't remove points if you don't. That gives us our positive charge on our oxygen, making our oxygen a good leaving group. So remember, our bromine is a pretty good nucleophile. So we're going to get the attack to then have this leaving group. So that forms our phenol. Plus this compound. Now, if this was anything other than phenol, we'd continue this reaction. Why did I put this leave as a negative charge? I'm sorry. I'm tired. That already has a hydrogen attached. So that forms our phenol and our other compound. Now, in any other compound, this is not the phenol, but if this was any other R group, we would then get another attack of HBr and then another breakdown. But because this is phenol, it stops. So this only happens when your benzene ring is directly attached to your oxygen. So let's pretend that this was this. Again, our mechanism. Our first step is the protonation because these are acidic conditions. So we don't form negative charge in acidic conditions. Our bromine can attack either of those partial positive carbons. And another thing to remember, these conditions are what we consider harsh. This isn't just a little bit of acid. We have a lot of this harsh, strong acid floating around. So that means that this breaks down pretty well. So since this is not phenol, this reaction would continue, and then you would get another reaction with acid. Remember, there's a lot of acid present. So you just get the second reaction again. And in this case, what you're forming is completely breaking up your phenol, and you lose water. So that's what would happen if you have anything other than phenol. And that would be your products. But we have phenol, so we stop here.
So you have to,
It's just the same mechanism twice.
you have to attack at the other.
This is just an SN2 reaction. This is an SN2 reaction. This is my leaving group. This is my partial positive carbon. That's my electrophile. Same reaction. And then it happens again. But here we stop because it's full. And that's the only limitation. And of course this doesn't work with HF and HCl. You would get no reaction. Another synthesis. In this case, again, you have a halogen. So you're starting with one. And we're forming a new carbon-carbon bond. And in this case, it's a double bond, but we haven't talked about any way to clearly form a double bond. However, we can do a Grignard, and then we can have our alcohol be a leaving group and form an E2 reaction. So that means our functionality was on the carbon that's directly attached to my new bond. So we can go through aceto bond. And again, at this point, we haven't talked about doing an epoxide. So it's not really an option, it's not even here. So our first step, because we can't make a triple bond out of this anyway, is to react this with our magnesium to form our Grignard. And then, and again, you can't really isolate this. We're going to react it. And we want the new bond between my ring and carbon 1. So that means my functionality has to be on carbon 1. So here my functionality is on carbon 2, plus it's an alcohol and we can't react a Grignard with an alcohol. We just discussed that the Grignard does not do well with alkyl halides, instead we get an E2 reaction. And even though the connectivity is right here, this is an alcohol, so we can't react our Grignard with an alcohol. Here we have acetyl bond O, but my new bond would be between my ring and carbon 2. But that's not where I want my new bond to be. So think about what that reaction would look like. Again, here's my Grignard reagent. If we reacted it with this example, we would attack carbon 2 because that's where my functionality is. So my new carbon-carbon bond would not be in the position that I want it to be in. And let's not forget my alcohol. So that, there's really no way to get from this to our product because the attachment's not right. So we're using this structure. I won't be giving these carbon sources for the final, but I will have them on the test tomorrow. It just makes it easier for me to grade. And then, of course, a little bit of water. So that's going to form my alcohol on carbon 1. It's not quite my product, but we can get to my product because we can make our alcohol a good leaving group and then react it to form an E2 reaction. So remember, tosylate makes our alcohol a good leaving group, not TMS. TMS protects it. So TS, Cl, and pyridine to make alcohol a good leaving group. And then we're just doing an E2 reaction. Are we forming the most substituted double bond or the least? Forming the most, so we need our strong, small base. Just to do our E2. So again, applying things that we have learned. Okay, last quiz. The one from the other day, I'm sorry. I started grading it and I tried, but I just didn't have the time. And it's probably, honestly, the quiz is probably not going to be graded for the drop date. I'm more concerned about your exam. You can still get a pretty good idea of how you've been doing on your quizzes. So I don't think that's going to affect your decision to drop or not based on what one quiz grade is. Because I keep everything pretty updated. So I'll try, but I'm not promising that that quiz will be graded. Because I'm not going to get home tonight till probably 9:30, 10 o'clock. Because I'm giving a 105 review after this. Okay. So, cumulated is this. We have that shared carbon. We don't see any of that in here. There's no cumulative. One carbon, two different pi bonds. That's a very distinct bonding. We don't have that. We have an sp3 carbon here, so this is going to be isolated. But these 3 pi bonds are in fact conjugated. Even though there's a nitrogen in there, it doesn't matter. We still have 3 conjugated pi bonds. And in the pi bond conjugated system, there's 2 electrons in every pi bond. We have 3 pi bonds, so that is 6 pi electrons. Yes, there are lone pairs on this nitrogen, but it's not involved in that pi bond because that pi bond that is in conjugation with the other 2, that p orbital, is already full. So those electrons that are on the nitrogen are what we consider localized, whereas the other electrons, the ones in the pi bond, are delocalized. So remember that from Organic 1. You never can forget anything we learn in this class because it's all applied, including everything from Organic 1. So looking at this one, we have lithium aluminum hydride. Remember, whenever you see this, this is a source of H negative. H negative is a pretty strong nucleophile. It's also a pretty strong base, so we consider this basic conditions. We won't form positive charge. So under basic conditions, we always get attack at the least substituted carbon. So that means we're going to get attack at carbon 1. When we attack carbon 1, we can't have 5 bonds to carbon, so that opens up the ring. So our oxygen is still attached to carbon 2. Nothing changes with the stereochemistry of carbon 2. So we still have a methyl group coming forward. We still have this isopropyl group going back, and of course we have our alcohol. You do not have to draw this hydrogen, but in the key I'm going to upload, I am showing it just so you see where it is. This is not a stereocenter because there's 2 other hydrogens attached there, but I just want you to see where it is. If this was a Grignard, you'd have the same reaction. If this was an OH negative, you'd have the same reaction. So it's just a matter of, here you have a new hydrogen-carbon bond, because that is a source of hydrogen nucleophile. So you didn't have to draw that hydrogen, but the alcohol is attached to carbon 2, and nothing changes with that stereochemistry. If, and this wouldn't be ever the case with a hydride attacking, if we're attacking our least substituted. But let's say it's a Grignard. If that is a stereocenter that it's attacking, it's going to lead to the inversion because it's SN2. But it's not, so that's irrelevant. But the carbon that gets attacked, if there is a stereocenter, it's going to be inversion. Okay. For this one, this is one of those examples. It's just so pretty. They have such good handwriting. I wish I was better, but I'm not. I don't have neat boxy handwriting. So with these, we have our we're still getting just an addition. Hydrogen's going to add to one of the pi bonds. But you're always going to form the intermediate where our resulting carbocation is in resonance, because that's more stable than a carbocation that's not in resonance. So in the example that we're looking at, the first thing you want to do is consider all your possible resonance structures. So we can have the addition of our hydrogen to carbon 1, and that's going to lead to a carbocation on carbon 2. So this is if H was adding to carbon 1. Still have my double bond between 3 and 4 because my H added to carbon 1. That leaves my carbocation here. on carbon 2. And then we do have resonance structure because that is in conjugation. Now this would lead to the same product, both of these resonance structures, but let's continue a little bit further. Our other option is hydrogen adding to carbon 4. So if our hydrogen adds to carbon 4, then the double bond between 1 and 2 is retained, and we have the carbocation on carbon 3. And then this also has a resonance structure. And I'm showing this hydrogen just so you can see where it added. It's not necessary to show that hydrogen, but I'm just showing it so you can follow what I'm talking about. So that's our other resonance structure. Now, if our hydrogen added to carbon 3 or carbon 2, that would lead an isolated carbocation that's not in resonance, so that's not going to lead to our major product, because the carbocation in resonance is more stable. So we don't even have to look at the possibility, because if we added hydrogen to carbon 2, that would leave my carbocation on carbon 1, and then we would not have resonance. So since that's the case, we don't care. It's not useful. So these are our possible intermediates. We have 4 things that we're looking at. If we were not using specified conditions, then you would get all 3 products. And I say 3 products because these 2 lead to the same product. They're the same. But this is a distinct product, and this is a distinct product. And really, it's look where the CH3 group is. Here, your bromine would be right next to the carbon with the CH3 group. Here, your bromine would be opposite. So those are different. Also note, they all form stereocenters, and you will get both enantiomers. However, the conditions are specified, and they're specified of 0 degrees Celsius. So that means that we're only going to be able to get over the lowest activation energy. So this low temp is going to be our kinetic product, the product from our lowest energy intermediate. We have carbocations, so basically it's going to be the product from our most stable carbocation. So what do we have? We have secondary, again that leads to the same product anyway, tertiary, and secondary. So at low temperatures, we're going to form the product from our most stable carbocation, which is our tertiary. So the bromine's going to attack that carbon. Now that will form both enantiomers. If I had higher temperature, about 40 to 50 degrees, that would be able to get over both activation energies, and we would get our lowest energy product, which means our product with the most stable double bond. Now we can't really go real high temperatures because this is an addition. Remember, addition is favored at low temperatures. But let's say about 40 to 50 degrees Celsius is what you're usually looking at, and that's going to be your thermodynamic product. And for your thermodynamic product, it's going to be your product that has the most substituted double bond. So this is tri-substituted, this is di, and this is tri. You'd actually form both of these. But you wouldn't form this one. That one's unstable. And remember, these 2 things lead to the same product. So you wouldn't draw 3 different products, just 2. So pay attention to your temperatures. You have to spend a little bit of time with this one. And honestly, I'm sure there's some people that can just visualize it. I have to write it. So write it. You're going to have scratch paper. Play around with it. But remember, we won't form the addition that'll lead to our carbocation that's not in resonance. So we only care about these. Okay, here. Sulfur stabilizes the negative charge better than oxygen. So when we react something like our NH, none of them work. That one works. So when we have something like our sulfur plus our OH negative, this is just our acid-base reaction. Remember, the equilibrium lies to this side because sulfur is bigger. So that's all that happens. So now we have, this was an okay nucleophile, this is a great nucleophile. So now we have an S nucleophile, and we have a reagent to react with, which is our alkyl halide. Now sulfur isn't a great base, even S negative, because again, this is pretty stable. So you don't have to worry about with the secondary alkyl halide an E2 reaction occurring. We'll just get the normal S into it. Unlike if this was an O negative or an O negative is the most common one, then we'd get the E2 reaction. We don't have to worry about that with sulfur. So we're just going to get the SN2 reaction, we're going to get inversion of stereochemistry, and we're going to get the attack at the partial positive carbon. So we just get our inversion. And that's it. It's just an SN2 reaction. We do a lot of SN2 reactions. That's why we spend so much time in chapter 7. Now, peroxide is a pretty strong oxidizing agent, so it's going to fully oxidize this. So we're going to get the structure I don't know why I put that in red, with our fully oxidizing. If we only want one sulfur oxygen double bond, we have to use the iodine containing oxidizing agent. So I only told you one oxidizing agent to do with that one. Okay, and this next one, the answer is not pericyclic because electrocyclic, sigmatropic, and cycloaddition are all examples of pericyclic reactions. So notice that we're starting with 3 pi bonds, and we only have 2 pi bonds. So that means we lost a pi bond and we gained a sigma bond. So this is an electrocyclic. A sigmatropic rearrangement means that we have the same amount of pi bonds, both the starting material and the final product, because it's just a rearrangement. And an addition means we're taking 2 molecules and adding them together. So we're only starting with 1 molecule, so this is not an addition. And in addition, we're losing 2 pi bonds and gaining 2 sigma bonds. So that's not happening here. So this is an electrocyclic reaction. And the mechanism is just the same mechanism as concerted. We're forming a new sigma bond between this carbon and the in carbon. That pi bond has to be shifted and here. The reaction only happens between the conjugated double bonds. Don't worry about the R group that's attached. Only pay attention to those 6 carbons. This can be 50 carbons, it doesn't matter. We're only looking at this. It doesn't matter what those R groups are. I mean, I'm not going to say it doesn't matter, it can affect reactivity and things like that, but in general, for what we're doing in here, it doesn't really make a difference. Okay, this is really easy. Label diene, label dienephile. What does the term diene mean? 2 double bonds. So, this is my diene, because it has 2 double bonds. If I were to name it, it would be named a diene. That's how I would name it. I mean, the parent name would be pentadiene, because it has 5 total carbons. My dienophile is the thing that loves the diene. So that's the other thing. So this is my dienophile. Now don't get confused with the carbon-oxygen double bonds here. The purpose of this is our electron withdrawing groups to make our dienophile more reactive. Also notice they're trans to each other. They're trans to the pi bond. That means that they're going to be trans in the final product. So the reaction is between carbons 1, 2, 3, and 4 of our diene. Don't worry about those CH3 groups. They don't matter. Which are going to react with carbons 5 and 6 of our dienophile. Because the Diels-Alder reaction always forms a 6-membered ring. So that means you're reacting 4 unhybridized p orbitals with 2 unhybridized p orbitals. So that's the definition of the Diels-Alder reaction. So here's my 1, 2, 3, 4, and 5 and 6. So we formed a new bond between 1 and 6, and 5 and 4, and that pi bond between 3 and 4 had to be moved between 2 and 3, because otherwise 4 would have too many bonds. So there's my double bond, and here's my new carbon-carbon bonds. Does everyone see that? Okay, now I just have to put in my R groups that are not actually reacting. They're just hanging out. So on carbon 1, I have 2 methyl groups. There they are. They're just hanging out. Just go there. They're not participating in the reaction, so they just end up in the final product. Carbon 6, I have my electron withdrawing group, and carbon 5, I have my electron withdrawing group. But they will be trans to each other, so I do have to specify that. And we will form both enantiomers, because we're going to form both trans enantiomers. We're never going to form the cis, because my electron withdrawing group started out trans to the original double bond. If I draw a line, they're on opposite sides. But this is the basic reaction, no matter what is attached to it. So that's our basic reaction. I'm finishing up with this. Y'all can sit in, learn some organic chemistry. But
Oh, and I thought it was late. I was like,
no, we started 6:15.
oh.
This is 1:05. Y'all can hang out and listen to it if y'all want. It's not going to be on your test. Okay.
That product is benzene, right?
No. Benzene ring is 3 alternating double bonds. This is different.
It's just like,
This is a cyclohexene. So this is the basic reaction, and I'm just putting in the R groups that are attached. Also, if this was a triple bond, we would retain that double bond between 4 and 5, because we're only using 1 pi bond. So that dienophile can be a triple bond. And that triple bond, one of the pi bonds is retained. If it starts out with a triple bond. Another Grignard reaction. But this Grignard reaction is slightly different in the fact that my oxygen is not on the same carbon as my new carbon-carbon double bond. I mean carbon-carbon single bond. So here's my starting material, carbons, and these are my new carbons. And notice my new bond is between carbon 1, but my functional group is on carbon 2. So as soon as you see that, you should think of oxide. We're going to attack the least substituted carbon. It's going to open up the ring, so our alcohol is on carbon 2. If we reacted it with this, my alcohol would be on carbon 2, but my new carbon-carbon bond would also be on carbon 2. That's not the right connectivity. Because our Grignard attacks the electrophilic carbon. So that's not the right connectivity. Again, we can't react the Grignard with an alcohol. The Grignard doesn't react well with an alkyl halide because we get the E2. And this won't lead to the, it doesn't even have a cyclopentane ring. So clearly those are not reagents. Now if we reacted our Grignard with this first one, then our new carbon-carbon bond would be on carbon 1, but so would our alcohol. So we're going through the epoxide because of connectivity. Have a good night. So our first step, we gotta make this a Grignard. Throw in some magnesium. Then we're going to react it with our epoxide because of connectivity. And remember, under the basic conditions, we react with our least substituted. So that forms our new bond between carbon 1. And that leaves our alcohol on carbon 2. We need water. But believe me, even if you don't add in water, once you expose it to air, it's going to find a proton from the air. So it would do this whether you put in water or not. Typically, you want a little bit extra water to use up your Grignard reagent, because if you do expose it to air, it could catch on fire because it's really reactive, so you got to be careful. So you would add water typically pretty slowly drop-wise, because it's going to be very exothermic. I know I say things catch on fire, but I'm serious, they do. You don't usually think about adding water to stuff and it catching on fire, but it can happen. So you got to be careful. The more reactive, the less selective. Now this isn't our final product because we need to do an oxidation to get the ketone. So it's a ketone. We can use PCC or chromic acid. We only have one hydrogen, so it doesn't matter. That would work either way. I'm hungry. I don't think this is a healthy meal, but it was very yummy. Okay, the bonus ones we went over in, well, this is not a bonus. So let's draw this one. And don't worry about the R groups. Have a good night, Taylor. These two, we don't care about them. They're sp3 carbons. You can tack them to the end of the diagram, but we don't need them. We're only representing the unhybridized p orbitals. We have 4, so that's how we're going to represent. So we have 4 unhybridized p orbitals in conjugation. So that's our atomic orbitals. We have 4 atomic orbitals. So our molecular orbitals are going to equal to our atomic orbitals, which means we're going to have 4. Our lowest energy one is going to be completely bonding with 0 nodes. Our lowest energy always has 0 nodes. As we go up in energy, we increase the nodes. And we never have degenerates, so we always have different energy levels with these. So our lowest energy one and our highest energy one is the easiest to draw. Because the lowest energy one, we have no nodes, meaning red, 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 red up. They're completely, the electrons can be shared between all p orbitals. Our completely anti-bonding is going to have our total most number of nodes. So that's 3. So it's going to be red up, red down, red up, red down. That means that we have a space of 0 probability that the electrons will be there. So we have 1, 2, 3 anti-bonding interactions. Now, again, you're going to be shading this. Sometimes in the book it's represented as red and blue, but that's irrelevant. All that's representing is that big mathematical equation that either gives you a positive one or a negative one. For the interaction to occur, you have to have a like interaction. So that's all that's representing. Now the middle ones are sometimes a little bit harder, but they're going to be symmetric. So we have one node. The only place to put one node and still have symmetry is right down the middle. So red up, and then once we get to the node, we alternate. Now you can start with red down, that's irrelevant, as long as the shading's all on one side until you get to node. So again, the red just represents that they're all alike, and the unshaded just represents it's all alike. And then this one is 2 nodes, so the only way to allow symmetry is to have them here. So every time I get to a node, I alternate. Notice the more nodes, the higher in energy. These are bonding because we have more good interactions than bad. This is a bad interaction. And then when we have more bad than good, then it's anti-bonding. If we had an equal amount, it would be non-bonding, but we won't have that with these even number of pi bonds.
So the way you start this is, what did you circle on the beginning?
That-
What's not?
That's just what's not interacting. We're representing our conjugated pi bonds. That's all we're representing. And remember, sp2 carbons have an unhybridized p orbital. So we're only representing the pi bond, the unhybridized p orbital. The sigma bond, we don't care about it, we're not representing it.
And you have to always start with 0 nodes, right?
Yes, with these linear systems. So if we had 6, let's say we had 6, let's say it looked like this. We have 6 unhybridized p orbitals, so we're going to have 6 unhybridized molecular orbitals. And they're going to increase.
Six times.
Yep. And then we'll have 0, 1, 2, 3, 4, 5. The lowest will have 0 nodes. The highest will have all alternating, so all bad interactions. And then in between, we're going to have some symmetry. And sometimes with the 6th one, whoops. You can erase. Yeah. Anyway, so continuing with that. If I gave you 50, you'd have 0 to 49 nodes. I will not give you 50. That's not something.
And just make it the only problem.
The only problem on the test. I don't even know if I could. I don't even think I could mathematically figure out what the nodes would look like with 50 because of the symmetry would be really confusing. But, and again, this isn't completed, so look in your book to see the completed thing. I won't ask you anything more than 6. Just a single double bond, then all we have is completely bonding and completely anti-bonding. That's the easiest one. That's your dienophile. Okay, so we're not done. We have to put in our electrons. Again, we're only putting the electrons in the pi bonds. We have 2 pi bonds, so that means we have 4 electrons. Remember Aufgu's principle? We fill until we go up to the next energy level. This is our ground state representation. So under heat conditions, this is what it looks like. If we use light conditions, we promote from here. We promote 1 electron to the higher energy level. Now that relaxes really quickly, but that's light conditions. And that's what we call the excited state. Under light conditions, this is our highest occupied molecular orbital. This is our lowest unoccupied molecular orbital. Because it doesn't have to be a filled orbital, it just has to be the highest energy orbital occupied. And when I say highest and lowest, I mean energy. So for the ground state conditions, this is our HOMO, our highest occupied molecular orbital, and this is our LUMO. And again, we mean energy-wise. We always draw energy from 0 to up. That's true in our reaction coordinate diagrams. It's pretty much always true. So we can use that to help us with the bonus. And that's our last thing to do. So with the bonus, all we're doing, this is electrocyclic. So this is only a reaction between carbons 1 through 4. We're going to form a new bond between carbons, have a great night, 1 and 4. And then the double bond gets put between 2 and 3. This is very similar to this reaction, except this reaction had 3 pi bonds, so we have 3 arrows, whereas this reaction only has 2 pi bonds. But it's pretty much the same reaction. So we lose 1 pi bond, we gain a sigma bond. So it's an electrocyclic. Also, the answer to that answer on the first page was electrocyclic. I gave it to you right there. I answer almost half your quiz questions on the quiz. So the question is it conrotatory or disrotatory? When we form this new sigma bond, remember our p orbitals are side-by-side overlap, but our sigma bond orbitals are head-on overlap. So our p orbitals have to hybridize to form the sigma bond. But only our p orbitals on carbon 1 and carbon 4 have to do that. So what we want to do to understand this is we can take this HOMO and just redraw it on our starting material. So carbon 1, again, we're using this. So here's my node. So all I did was redraw it in the same way that this is oriented, just so I can see it better. But it's the exact same thing as this. Here's my 2 red is up, my 2 red are down when I hit the node. So that's the same thing. We really only care about the 2 carbons on carbon 1 and carbon 4. So I like to redraw this for ease in looking at it with my carbon 1 and carbon 4 coming towards me, because it's just a little bit easier to see the orbitals. Again, here's my node. And I'm also going to redraw my R groups. So if I look at carbon 1, that CH3 group is pointed down. And if I look at carbon 4, it's also pointed down. So all I did was reorient this so I can see it better. So all I did was take this and flip it this way. Just so I can see. Okay, so for this sigma bond to form, these carbons have to turn so the pi bonds overlap. They're like this. Think of my wrist as being the carbon. We have to rotate so they can overlap. When they overlap, either my red and my red need to overlap, or my white and my white need to overlap. But red cannot overlap with white. So that determines which direction they can turn in. So let's say I turn carbon 4 clockwise. I don't really care about carbons 2 or 3. The pi bond is retained. So I rotated it clockwise, and that put my R group going up. So here's my thumb. I rotated. Now it's up. You see that? So which direction do I need to rotate this one in so my red can overlap? I also have to rotate it clockwise, because then my red can overlap. And this is what we call symmetry allowed. So my red is here. If I rotate it clockwise, my red is overlapped. Look at where my R group is. If I rotate it, it's also up. So this is cis. And the way I can redraw this on my sheet is this way, just because it's a little bit easier to see. So this is when we rotate the same direction, in this case both clockwise, this is conrotatory. If we rotate in opposite directions, it's disrotatory. And if you were to use the excited state, then you would have to rotate it disrotatory for red and red to overlap. Now you can also allow white and white to overlap, which means we'd still form cis, but my two groups would be pointing down. So we get both enantiomers. But what we don't ever get is the trans product. It's dependent on the conditions. So that's how you use the molecular orbitals to determine what products you get. Lastly, this is a sigmatropic rearrangement. So again, same mechanism, this cyclic mechanism. The easiest thing to do for this one is to number your 6. And what we did was form a new sigma bond between 3 and 2. Here's 3, here's 2, here's 1, 4, 5, 6. So we have a new sigma bond between 3 and 4. Our double bond is now between 5 and 6, or 5 and oxygen. And our other double bond is between 1 and 2. And then you just put in your R groups. Carbon 3 had an isopropyl, carbon 4 had a methyl, and carbon 2 had a methyl. But they're irrelevant to the reaction. You just put them in at the end. So ignore them and only look at your pi system. If I were to name this, this is a 3-3, because here's our bonds breaking and forming. So it's 1, 2, 3, and 1, 2, 3. So it's a 3-3, and it's containing our oxygen. So that's a specific named reaction. So that's it. Any questions? All right, y'all have a good night. I'll see you tomorrow. You can try to email me. I might look at it. I don't know. I won't be home till super late, so. I'll be putting up the keys and if you need to listen to this again, this will